I'm Graham Theisen, a reproductive endocrinologist at Piedmont Reproductive Endocrinology Group in Charleston, South Carolina, here to answer all your infertility-related questions. In my last video, we looked at genetic carrier screening, which is a screening that parents do to look for things that they could be carriers for, where if they're carriers, they're unaffected, but they could pass that on to their children. What we looked at last time was autosomal recessive conditions, where if both the parents are carriers for the same condition, then their kids would have a 1 in 4 chance of having whatever disease they both carry. But I mentioned in that video, there's another special subset of diseases that we look at that are passed in a different way. And those are called X-linked conditions because they're carried on our X chromosomes, one of the two sex chromosomes, either X or Y. So let's take a look at those conditions today, and we can understand how those are passed from parents to their kids. Just like with autosomal recessive conditions, to understand X-linked conditions, we want to start by looking at our own chromosomes. And specifically in this situation, we want to look at our 23rd chromosome, because these are our sex chromosomes, the ones that make us male or female. Now we know that for females, they have 2 copies of their X chromosomes. On the other hand, males, they have 1 copy of the X and 1 copy of the Y. So for the purposes of diagramming, we're going to go ahead and color code these so that the X's are pink and the Y's are blue. And this is going to help us track where the various chromosomes are going when we're making sperm and egg out of these chromosomes. And to think about X-linked conditions, what I want you to do is we'll think about one of the more common X-linked conditions called spinal muscular atrophy, or SMA. So let's imagine that this person, this female partner, has 1 copy of the SMA gene, which is on the X chromosome, that has a mutation. So we see that on the right, marked in red. And then she has another copy, which is normal, marked as green on the left side. So this person will be totally unaffected, would not have any symptoms at all, because even though she has a mutation in one of her SMA genes, the other copy is normal and makes the difference. So this actually acts very similarly to autosomal recessive conditions like I talked about in my other video, at least in women. On the other hand, in men, they only have 1 copy of the X chromosome. So that means they only have 1 SMA gene. And so what that means is they either have a normal copy, like this person does here, and are unaffected, or they have a mutation and they actually have the disease. And that's because they don't have a second copy of the SMA gene in order to make up the difference when they have a mutation in their 1 copy that they do have. So let's look at this couple here, where on top we have an unaffected male, so he has a normal copy of the SMA gene. And on the bottom, we have the female partner who's a carrier. So she has 1 copy of the SMA gene that has a mutation, which is in red, and then she has a copy of the normal, which is in green. So just like we have done in our other videos, we're going to split up these chromosomes and see what happens when these two have kids together. Each one of their chromosomes is going to go into either a sperm or egg. On top we have sperm, on bottom we have eggs here. And what we'll do is we'll individually mark each one of these to see where everything's going. So on the top, what we see is that each of these sperm get either an X or Y chromosome. The green X means it's an X chromosome that has a normal copy of SMA. The Y chromosome is in black because it doesn't have a copy of SMA at all. And then what you'll see with the female partners down here is that she also has half of her eggs have green X's, which means they have normal copies of the SMA gene. But she also has red X's, which means she has an X chromosome, or that these eggs have an X chromosome that carry the mutation of the SMA gene. Let's take a look at the different possible combinations between sperm and eggs for this couple, and what that would mean for each of the different possible children they could have. So here we have the sperm on the left. They either carry an X with a normal SMA gene, or they carry a Y with no SMA gene at all. On the top, we have the eggs, which either carry an X chromosome that has the normal SMA gene, or an X chromosome that has a mutation in their SMA gene. And at this intersection, what we can see is that on the top here, we have where a sperm with an X and an egg with an X came together, and that makes an XX embryo. Those will be our girls. And then on the bottom, where a sperm with a Y matched with an egg with an X, those will be our boys. So this looks a little bit messy, so I think we can clean it up a little bit by removing some of these images and just letting the color on top represent our girls. And then the color on bottom represents our boys here. And we can focus more on just the chromosomes and whether or not they carry a mutation or a normal copy of the SMA gene. So if we focus on the girls first, what you can see is the top left were girls that happened to get a normal copy of the SMA gene from their dad's X chromosome and a normal copy of the SMA gene on their mom's chromosome. So these girls are unaffected non-carriers for SMA, so they don't carry the mutation at all. On the top right, what we see is, again, they got the X with the normal SMA gene from their dad, but then from their mom, they got an X with the SMA mutation. So these girls would be carriers like their mom. They would be unaffected. So these girls, um, either the left side or the right side, would be unaffected and not have spinal muscular atrophy. If we look at the boys, though, remember, the boys are only going to have one copy of the X chromosome at all. So that means they only have one copy of their SMA gene. On the left, what we see here is that these boys got the Y chromosome from their dad, because that's what makes them boys. And then from their mom, they happen to get the normal copy of the SMA gene. So they also would not have spinal muscular atrophy. But then when we look at the bottom right here, what ends up happening is they, again, get Y from dad. That's what makes them boys. But they get the mutation in the SMA gene on their mom's X chromosome. So these boys would be affected and actually have spinal muscular atrophy. And so if you look at the full picture, what this shows us is that when this couple has kids, when the female partner is a carrier and the male partner is unaffected, then 1/4 of their kids, if you look at all their kids, will actually have spinal muscular atrophy, but that fourth will all be boys. So this is why for X-linked conditions, people typically think of it as being diseases that moms are carriers for and then pass to their sons.